Thermal analysis and temperature diagrams of power transformer. In the thermal analysis actually is quite complex. The temperature drops within the transformer, or temperatures at various locations within the transformers are calculated using formula derived from thermodynamics and fluid dynamics using experimentally derived coefficients. This is actual temperature distribution or actual temperatures at different locations inside the transformer are found using these. Ideal conditions for the transmission of heat actually are never met in practice. For simplifications, actually it is assumed that there is linear variation of temperature along the exchange surfaces. So, exchange surfaces means we have inside the transformer windings we have, and there is a tank, and there is a radiator, external cooling system. So, on all these exchange surfaces over the length, over the height, we assume that linear temperature variation. Actually, it is non-linear, quite complex, but we assume for simplicity linear temperature variation and identical thermal characteristics for all windings. And manufacturer tries to achieve these to obtain optimum sizing of a transformer. Temperature diagrams. The temperature diagram of a transformer is a graphical representation of temperature at various locations in the transformer with respect to vertical position, assuming linear variation along the height of various parts. It actually does not represent its geometrical shape of a transformer. Please remember, at various points, what are the temperatures, and with the height and how the temperature varies, that is what is depicted. It will be clear with after drawing few temperature graphs. So, in an actual transformer, suppose this is the tank of an actual transformer, and here radiator pipes are there, and here again bottom of radiator pipes. It's a depiction actually, not exact transformer. So, this is core, and then this is one winding, this is another winding, like primary and secondary. So, you have various locations here. Now, these radiator pipes have these cross connections also. So, this is a transformer typically, maybe say ON, AN transformer. Now, let us indicate various points in the transformer A. This is B. So, here what will be there? Here oil will be there in entire this empty space. This is one winding. This is another winding. Cross sectional view. Okay, this entire space is filled with oil. This dot dot. Okay. Other points in the winding, this is D, This is G at about the midpoint, and this is E. And hot spot is also close to the top portion of the winding, somewhere here F you can assume, and C is here in oil again. So at various locations, what is the temperature? Is the temperature distribution is given by what are known as temperature diagrams. The temperature diagrams are typically like this, and here this is bottom portion, say this is top portion, and here this point is say ambient temperature, and typically the temperature graphs will be like this. So this is say around 41 degrees centigrade, and this is 57 degrees centigrade, typically for O and A. This is point G, point D, point A, and B here, C here, and then E here, and F is here somewhere. So this is how the temperature diagram will look like. So A is around 41 degrees centigrade, you can see from the graph, and the B is around 53 degrees centigrade. This is in oil. So among these all other points, A and B are relatively on lower side, and C is also in oil, but you can see from B to C there is some certain distance, and C is expected to be at higher temperature, typically at 57 degrees centigrade. This is for O and A, and I am drawing. So, and then for D and E, this is actually winding, where both in the primary winding also, in the secondary winding also, the heat is generated. Wherever heat is generated, there highest temperatures are expected. So, from D to E, it is actually parallel to A to C, assuming linear variation, of course. In practice, it is non-linear variation. So, A to C temperature or A to B temperature variation, you can see here, and A to C is almost nearly parallel to D to E, but D to E is at higher temperature, 16 degrees centigrade. G is average temperature, roughly around 65 degrees centigrade. So E is at 73 degrees centigrade, and F is the hot spot temperature, which is 75 degrees centigrade. So this is how the temperature diagram of a transformer will look like. This is a ON-AN transformer. The temperature diagram given here is of ON-AN transformer. Oil natural, air natural. Means this oil will circulate through by natural convection only, through these pipes and then through the windings, and air outside this cooler is also cooled by natural convection of air outside. So this is what we have done. So you can see just now for ONAN transformer. There are no fans, you can see. Simply radiator column is there, exposed to outside air nature. So inside the tank also we have oil natural again. So it's a temperature diagram we have just now drawn, but I will redraw here for more clarity. This is bottom, this is top, and this is ambient temperature. And point A, just now we have seen point A is around 41 degrees centigrade. And point B means where the oil leaves is around 53 degrees centigrade. So bottom portion of the transformer is cooler actually, and the top portion is hotter. So from A to B, you can see it is a straight line fashion from 41 degrees centigrade to 53 degrees centigrade. And the point C is located here. Point C. This point C at a relatively little bit higher temperature, and its variation is like this. This is around 57 degrees centigrade. So this is point C. And AC is parallel to DE, which is DE is actually winding copper portion. Bottom to top, it will be like this. This is point D, which is roughly 57 degrees centigrade. And the top point is E, which is 73 degrees centigrade. And the hot spot temperature will be around, it's denoted by F, and around 75 degrees centigrade. So this is how typically the temperature diagram of ONAN transformer will look like. This is temperature. See, the horizontal axis is temperature here. The vertical axis is top to bottom, vertical position. Vertical position is alright, but you know, the temperature diagram does not, graphically depict a physical geometry of the transformer. Do not get confused here. The x-axis is only temperature axis. It is not a physical position. Then ONAF transformer. As you know, ON, inside there is no change, oil natural. Outside air force. So as you see here, these fans, two fans you can see here, are extra compared to ONAN transformer. What will happen with this? With the use of fans, the coefficient of transmission between oil and air can be increased. Oil is inside the tank and which will flow through these radiators and exchange with the outer environment or air. So when you force the air using the fans, the transmission coefficient will increase. The transmission may reach 100%, depending on the situation, of course. For about same average temperature of the copper as in ONAN transformer. For example, the maximum temperature is one limitation and the average temperature is another one. So for same average temperature as that of ONAM, the ONAF means air force transformer power can be increased by about 25%. This is important. So around additional power of 25% extra power can be handled by the transformer by use of these fans. So this causes the copper oil temperature gradient in the windings, and from top and bottom of the cooler windings to increase. Why it increases? Temperature gradient increases because additional power we are using now. If the power increases, obviously heat loss increases. When heat loss increases, it is a thermal circuit. It is a kind of thermal circuit. You have the thermal resistance. So thermal heat is actually analogous to current, and thermal resistance is analogous to electrical resistance. So current multiplied by resistance voltage, that is temperature gradient, that increases in this ONAF transformer if additional power is to be supplied, because it can handle additional power. Therefore, this is to be this will happen inside the transformer. So this must be compensated by lower average oil temperature because the gradient increases. So therefore, oil average temperature should be smaller, because we cannot increase the temperature of the copper. So if the gradient is more, it has to be that the oil temperature has to be low. And let us see the ONAF temperature diagram. So this is like this actually. So since the the outer portion, the copper portion, has to be maintained more or less same as the previous case. So let me draw first the outer portion. This is 53 degrees centigrade and 73 degrees centigrade E, point E. This is point D. And hot spot temperature is around 75 degrees centigrade. Now there is more drop from copper to oil. This is around 20 degrees centigrade. Say. These are parallel actually. This is A again. This is around 33 degrees centigrade. This is to be 20, and here it is 53 degrees centigrade. This is point C. And then AB is like this somewhat. B is around 48 degrees centigrade. So this is how various temperatures at various locations in ONAF transformer will look like. So the only difference here is 20 degrees centigrade is the temperature difference between copper and oil, and then there is a difference in lower temperatures also. Oil temperature A and B are now 33 degrees centigrade and 48 degrees centigrade instead of 41 degrees centigrade and 53 degrees centigrade in case of ON-AN transformer. Next is OF-AF. Now in the last transformer, fans are added. In this, oil is also being forced. So you can see at the bottom of this transformer there are pumps actually which will cause circulation of the oil. More intense cooling of the oil increases its viscosity. Suppose last time we have seen fans using fans. If we go on reducing the temperature of the cooler, then what will happen? Oil viscosity will increase, and this restricts the circulation of the oil, natural circulation of the oil, and limiting the increase in power. Therefore, there is a limit using just by fans. Therefore, for improved performance, an oil circulation pump must be used. So, these pumps are used in OF-AF transformer. The transmission coefficient, of course, increases further, and the difference of T from top to bottom reduces. Now, this is important. See, in the previous case, temperature gradient increased. The oil was not circulated, only outside cooler was used to decrease the temperature of the oil. So that increases the gradient between windings and oil if the operating power is to be increased by 25% roughly. So by maintaining the temperature of the winding same. So oil temperature, between oil temperature and winding temperature, the gradient is more. But here in this case, oil is being circulated now. Earlier, the oil is circulated by natural convection. In this, forced by using pumps, we are circulating. Therefore, from top portion and bottom portion, difference between top and bottom decreases or reduces. Then the circulation of the oil within the windings always occur by convection. Of course, one thing we have to remember, if you use just only pumps, oil will circulate inside the transformer, sure, but inside the windings, windings are copper strips or coils, so and they are supported mechanically by mechanical spacers. So through that actually oil circulation will be low only. So most of the oil circulated by pump flows in the tank around the outside of the windings, not through inside the windings. So this is the difference between this transformer and the next transformer that we discussed soon. So this is about OF-AF transformer. So in this oil is circulated, but within the windings oil will not circulate using the pumps, but it happens through natural convection only. Little bit difference may be there. As per the temperature diagram of OF-AF transformer, so it is like this actually. Again, you please recall what are A, B, C, D, etc. So this is again temperature, and this is again vertical position. Here this is bottom, this is top, like this, and then let me draw that 53 degrees centigrade, and this is 73 degrees centigrade, and here it is 75 degrees. Here, why this is happening, you have to understand here. Through the winding, there is no difference actually. That is why, and winding is the hotter portion. Therefore, it dominates in deciding the temperature within it. So 53 to 73, more or less same as the previous case. even though oil is circulated now. But within the oil there will be huge difference. So the point C will be again at higher temperature only. So the difference is more or less same. So this is 33 degrees centigrade and this is 53 degrees centigrade. This is point C, this is point A. But point B will be cooler. Around 41 degrees centigrade only. This is again 20 degrees centigrade. Why this is happening? This is point B. Because most of the oil is getting circulated through the outer portion of the winding. Now let me draw roughly the transformer here. So here this is winding 1, this is winding 2, and here radiator columns are there like this. What is happening? You are using a pump here. This is a pump. So oil circulates in this path mostly. Therefore, the temperature, this is point A, if you remember, this is point B. So A and B temperature falls, compared to C, which is close to the windings, and the circulation within the windings is less only, D and E. So therefore DE remains more or less same. Of course, some additional improvement in the power is possible with this arrangement. Then the next one is, the final one is ODAF transformer. The final step is to channel the oil leaving the cooler so that it flows towards the base of magnetic circuit and the windings. So instead of allowing it to flow freely in whichever direction it flows, if we channel the oil leaving the cooler so that it flows towards the base of the magnetic circuit, then that is what is known as directed flow of the oil. The velocity of the oil in the windings now could be increased around 10 times, and this practically doubles the coefficient of heat transmission. This is very, very important. Now the temperatures are very much uniform along the vertical position. Therefore, average temperature can be increased now with the same hot spot temperature. See, basically hot spot temperature is the concern where the maximum aging could take place. Therefore, now if winding temperatures are uniform, means everywhere the more or less the temperature is same. So we can go close to the hot spot temperature. All other layers of the winding also can go close to the hot spot temperature. Means average temperature will increase. If average temperature increase means what? Average power dissipation can increase. Means what? The power transmission capability increases. This arrangement is used more and more in medium power transformers, so 10 to 100 megawatt, and is universally used in high power transformers greater than 100 megawatt. Now the ODAF transformer temperature diagram like this. Since uniform temperatures are attained here, so the points D and E, of course, for increased power, of course, power can be increased. Then this is bottom, this is top, and here the point D is around 68 degrees centigrade here. Now here, and then this is 73 degrees centigrade, and then here the hot spot temperature is around 74 to 75 degrees centigrade. This is F, this is E. Now since the cooling is efficient now, even in the inside the windings, the difference between bottom and top is decreased. This is 68, you can see, and this is 73. Earlier this was 53. The bottom D point was at 53 earlier. Now the difference between winding and oil also decreases actually, and it is around 15 degrees centigrade. And this is A, point A, 53 degrees centigrade. And here there is no difference between B and C because of the circulation of the oil. It's around 57 degrees centigrade. Both B and C will be here. So this is how the ODAF transformer temperature diagram will look like, and this is the final arrangement in which greater power can be circulated, power can be handled by the transformer. So therefore, outside you have fan cooled, forced air cooling, but outside even water can also be used. That is also forced water cooling is also possible. So, but inside having directed flow of the oil, we can achieve greater power density in the transformer.